As promised, we're sort of going to now talk a bit about group activity recognition and scenes of people. So to set the context of what we're going to be talking about, I said in the morning how we really wanted to emphasize what's going on overall in a picture, being able to localize actions and so forth. So if you take an example, if here's a frame from a video of some people in a nursing home facility, what would we like to do when we say we want to do activity recognition? One of the key problems we want to solve that I talked about this morning is spatio-temporally localizing actions. So I'd like to be able to go in and on this frame of video say, here are some people, this one's standing, this one's running, this one has fallen, this one is squatting. But beyond that, there are a lot of other things that we could ask about. We could ask, where are they? So knowing, as many of the other previous speakers have pointed out, knowing where the people are and what objects are around is very important when it comes to understanding human activity. So for example, I'd like to know that they are in an indoor scene. This indoor scene is a long-term care facility. This person's lying down on the floor. There's a chair behind this other person. Again, knowing all the scenes and all the objects will help me understand this as an activity scene. Beyond that, we'd also like to answer, not just what actions are these people doing, but why are they doing them? So this person who's standing there is standing there and he's watching this scene. The person in the background, she's running, but she's running to get help. The person in the front, she's squatting and squatting to comfort the person who has fallen. So again, there are different labels that we can put on these people, not just the actions that they're doing, but some sort of intention or social role about why they're doing those actions. And then at a more holistic level, what's happening in this scene? Well, we're helping the fallen person. At a group activity level, that's what's going on in this scene. And all of these problems are really intertwined. I've got a whole set of labels that I wish to put on these. And when we say we want to do activity recognition, I feel like that's sort of the goal of this field. We want to really completely understand what's going on in this scene. And from that, if we can do things such as recognize all of the objects, recognize the scene, recognize the low-level actions, localize those on people, have intentions or social roles to figure out why they're doing that, we can answer all the questions that you might want to answer about this scene. Right? So that's sort of the view of what we're talking about. And in this part, I'm going to talk about models and methods that relate together the actions of individuals to understand what the entire group is doing. So there are a number of different application domains where this comes up. One of them is in this surveillance type setting that I've been talking about up to now. And for each of these different settings, we have data sets that are sort of the canonical ones that people use to try to evaluate algorithms. On the surveillance side, a few of the leading data sets are this collective activity data set from 2009 from Choi et al. There's a Virat series of videos that are sort of surveillance videos taken of parking lots, of street scenes, again, multi-person activity, again, in the context of surveillance videos. The UT interaction data set is sort of two-person interactions. Ryoo and Agrawal did this in 2010. Another place where this group activity analysis comes up a lot is in sports analytics. This is a very sophisticated area these days. There are a ton of companies that are out there collecting data on what people are doing in sports games, using this for predicting events, which players to draft, which strategies to employ. It's actually a very well-developed area of study. In the division community, we have a couple of data sets that people have used. Some students of mine and I collected a data set of volleyball videos. Vignesh Ramanathan has a data set of NCAA basketball games. So there are a number of other data sets out there as well, but people in sports contexts often care about sort of group activity recognition. Another domain where understanding groups of people comes up is in robotics. For example, building social robots that know how to live in an environment that's populated with people. So there's the Stanford drone data set, the sort of aerial imagery of trajectories of people, and you can use this to do things such as find a path through a scene that will be minimally invasive for the people that are living in that environment. The ETH and UCY data sets are similarly sort of pedestrianish data sets that can be used for modeling crowd flows and behaviors in those scenes. Okay, so a lot of the work that we've done is kind of in this sort of sports analytics domain. And analyzing a group of people and understanding what all of them are doing helps to answer a lot of really important questions. And so I'm from Vancouver, and people have spent time in Canada. There's a really hard group activity recognition challenge that you need to do if you're new to Canada, which is figuring out who has the puck in a hockey game. So if you look at this scene, I don't know if you can tell who is it who has the puck right now. Which player? I guarantee you that there's 0 puck pixels. so that you can't actually see where the puck is, but from body configuration and pose, it's the person on the near side in the lightly colored uniform is the person who currently has the puck. And we've actually developed algorithms that can do very similar types of reasoning. This is actually older work from 2012, where the player highlighted in pink is the one that we think right now has the ball in this field hockey match. And this is older work, so it's based on sort of hog features, handcrafted things. But what we can actually do is label this scene at multiple levels of detail, detecting all the people, putting action labels on them, so localizing them in space and time, what they're doing, as well as sort of in the top left is sort of the group activity, what's happening in this scene right now as a whole. So more recently, I'll just quickly highlight a few of the kind of recent methods that have been developed in sort of the deep learning era for modeling group activities and interactions between people. So in 2016, there were a few papers that worked on hierarchical LSTM, or recurrent neural network architectures, for analyzing human behaviors of many people in a scene. What most of these methods looked like was that you would have detections and tracks of people in a scene, and these are shown on this vertical slide, person 1 through person n. Each of these people, you could put them through an LSTM that would be able to recognize the individual action of that one person in the scene. So these could often be models that were trained specifically for human action recognition, for example, walking, running, standing, jumping, etc. You could have action labels that go on the individual people in the scene. Those would be aggregated in time via an LSTM. And then what you could do is aggregate over the entire scene by piping those through some sort of aggregation network. And these would range from things that would be sort of spatially relevant to things that were just sort of globally scene-wise, doing max pooling or mean pooling over the people in the scene. And again, you could feed those through another recurrent neural network that would capture at a sort of entire scene level what types of activities are persisting in the video over time. So these kind of like hierarchical LSTM models, and Mustafa, one of my students, developed one of these in CVPR18. There were a couple of other contemporary pieces of work. Again, one from Vignesh Ramanathan that was building similar types of models. His domain was analyzing basketball videos. And what you would do in this work is you would add to this an attention model. So you'd add something that would focus on some key player or key actor who is present in the scene. And, in this LSTM-based model, you could have sort of attention weights that would focus on the person who you think was important. So in a basketball game, that might be the player who has the ball, for example. You might be able to hone in on that person and develop features that sort of focus in on that person, weight those more heavily when you pipe them through LSTMs. Another piece of work, again, at the same CVPR a couple of years ago, was on building pooling methods, so aggregators, that would be aware of nearby people. Right? So in that hierarchical LSTM model that I mentioned, what you would have to do is sort of over time build a latent representation, so your hidden state vector H in an LSTM, build one of those for each of the people in the scene. In Alex Alehi's work, what they did was they said, let's build that representation per person and have a sort of social pooling or social LSTM model that says, I will pool features for this person that are based upon the people who are nearby, and I can quantize the sort of the bins of nearby people. Right? So for this one particular person in a scene, I could say people who are up and to the right of them, those features for those people we pooled together when I make the updates in my LSTM model. And so that's what's called a social LSTM, and it's a way to sort of, in a scene consisting of lots of people, particularly in these trajectory data sets where you might have groups of people who are walking together, you can pool people's features who are spatially nearby. Okay, so this is sort of a trend of work that exists in our community, sort of, looking at how we aggregate features over multiple people in a scene. Recently, we've done some work on using this to analyze trajectories, and really from real basketball games. So from trajectories such as these, could you answer questions such as, the team in blue, which team was this? All right, so you're just looking at the trajectories of the players. Can you answer a question such as that? Or other questions, will the shot be successful? Or what's the next event that's likely to take place? Is there likely to be a 3-point shot or a 2-point shot? What's likely to happen next in this scene? Again, purely from just the trajectories as input. And these days, we've got a lot of successes in our field, and the problem of taking a broadcast video, detecting all of the players, tracking them, putting those tracks in 3D world coordinates, or in this case, or 2D on a ground plane from a broadcast video, it's basically a solved problem. So, there are companies out there that will do this. You can take in a broadcast video, estimate homography matrices to map those to real-world coordinates, do faster RCN or other types of automated human detection algorithms, track those, and we can get trajectories that look very, very clean out of that. So going beyond this now to figure out what can we do with this, what can we understand about this behavior. So we built something that we published earlier this year at the Sloan Sports Analytics Conference. This was sort of a fully convolutional, sort of temporal convolution network style approach to taking those trajectories of players, piping them through sort of conv layers that would end up learning stereotypical little bits of motion. So for example, we could have a person who's walking in a straight line, a person who's walking and making a cut to the left, someone who sort of fakes to the right, then goes to the left. We could essentially learn conv filters that would capture information such as that. And what you can do is you can stack those up. So each of the player trajectories that's shown as one of those colored lines, you can pipe those through a trajectory network that will analyze what that individual person is doing, and then concatenate those together to get a representation of the entire team. And then similarly, you can learn sort of shared conv layers that would say, I'm looking for a pattern where player 1 does this and player 2 does that. And we can, again, learn layers of those sort of networks, stack them together. At the end of the day, we can concatenate those features together and classify this, either figuring out what the activity is that's going on in this scene, which team this is, etc. So we've done experiments using these types of models in a couple of different domains. So one of them is in NHL hockey. So we gathered a data set from, again, broadcast videos of NHL hockey games. State-of-the-art algorithms are used to automatically detect, track players, place them on rink coordinates. And then what we can do is take trajectories and figure out what event is taking place in those scenes. Right? So if you look, these are sort of some statistics from the data set. Events such as puck protection, so when you sort of prevent someone else from taking the puck away from you, carry over a line, shots, dump in, dump out, and passes. Again, there's usually huge imbalances in these types of data sets where passes are by far the most frequent type of event. And again, we use some games for training, some for validation, some for test. And what we can show is that by using these kind of trajectory-based networks where we learn to classify based on the trajectories, we can actually do better than methods that look at the visual features. Right? So C3D at this time was our baseline method that looks at the visual features. Just from the trajectories alone, we can figure out what the players are doing a few percentage points better than looking at the visual features that come from the bounding boxes of the players. Right? So here's some mean average precision numbers for looking at this, and we compare to some other trajectory-based baselines. So I mentioned about sort of NBA games and figuring out what team is playing. So we've also done experiments on NBA data sets. We used an entire season's worth of NBA games, 1,076 games. We extract out every ball possession. So ball possession is when one team has the ball and it ends in either a shot or a turnover. 137,000 possessions extracted from those games. And we sort of truncate the possessions to some length, 200 frames long. We use a bunch of them for training, validation, tests, etc. So the short of it is, it turns out that you actually can tell which team it is simply from the trajectories of the 5 players. How well can you do that? If you take a single possession, so just one NBA possession, which is maximum 24 seconds long, ask which of the 30 NBA teams was that, you get an accuracy of about 25%. So chance performance is 3%. There are 30 teams. If you just guess which team was this, it's sort of 3% accuracy. Just from the trajectories alone, you can get 25% accuracy. You can do some very naive things about aggregating that over time. If you just do a max voting over all the games, all the possessions in a game, you can get that up to sort of 95% performance. So again, these models are able to learn idiosyncrasies about the players' trajectories for a particular team and use that to get very good classification. We've done other things as well about predicting shot location. So here's a sort of breakdown of different places you can take a shot in an NBA game. These are sort of 14 different shooting zones. These are sort of, basketball analysts use this to sort of, look at different hot shooting zones and where people are taking shots from. So again, what we've done is we've used our trajectory type analysis modules to try to predict where is the next shot going to take place in the basketball game. So there are a couple of baselines that you could use if you're going to do this task. So if you're trying to predict where the next shot is in a basketball game, what do you think is a good baseline? Okay, you know the trajectories of all the players. What are some very naive, actually pretty effective baselines for this? Sorry? Most open player. That's a bit more sophisticated. Our method might learn something like that. So who's the most open player was one suggestion what you could do. So where do you think the most common shot is taking place out of these 14 zones? 0. So yeah, the majority, the pluralities, or the most frequent place where a shot takes place in an NBA game is right under the basket. Probably rebounds or layups or dunks or something like that. 0 is the most common thing. So one thing is you could always just guess 0. Zone 0, that's where it's going to take place. What's the other thing? Again, if you have the trajectories of all of the players and the ball, where do you think the next shot is going to take place? Where the ball is now. Okay, so those are kind of two very naive baselines. If you have to guess, where is the next shot going to take place? It's where the ball is right now or under the basket. And so we develop methods that sort of try to learn to predict where that's going to happen. This graph right here is showing the results. The horizontal axis is the time before the shot takes place. And you see that the coordinates are sort of negative. This axis here is at 0. So when the shot takes place, the baseline that predicts the ball position, which is shown in green, is perfectly accurate. Okay? The blue line is always guess under the basket. Right? So that has sort of an accuracy of about 30-some%. That fraction of shots take place under the basket. Our model is the one shown in yellow, and what it can do is it can kind of learn that, you know, usually if you're sort of far away from there being a shot when people are just playing around, just keep guessing under the basket, under the basket, under the basket. As we get closer to there sort of being a shot taking place, that accuracy ramps up where it's able to somehow guess ahead of time where things are going to take place. And it kind of has a little bit of a bias in it, so it doesn't perform as well as the always guess where the ball is right now. Right at the end, it kind of overfits a little bit today. That has some bias in the model. Okay, so that's something we can do is sort of predicting, again, by analyzing the trajectories of all the players. We can make predictions like this reasonably, you know, definitely better than the baseline type performances. We've also done things on modeling distributions over where things are going to take place. Right, so up here I'm showing sort of a sequence of events that take place in a hockey game. At time, 0.13 seconds, there was a pass event. At time 1.05 seconds, there was a receive the pass event. At time 2.26, there was a carry the puck event. At time 3.84 seconds, there was a dump in event. You could then ask the question, what's going to happen next? What event is going to take place next? When is it going to take place? And where is it going to take place? So this is sort of a discrete instantaneous time view of activity prediction or forecasting. So what exact event is going to take place next? Where is it going to take place? And when is it going to take place? How much further in the future? And this is actually a really reasonable model of many types of things that take place in the real world. So if you think about a lot of either sports gambling or measurements of performance would be things such as, who's going to get the next yellow card? When is that going to happen? If you're trying to predict population and what people are going to do next. Who's going to be the next one to call for an Uber? Where is that going to take place? When is it going to take place? So these kind of discrete moment versions of activity representations are quite powerful for these types of models. So there's some standard literature around modeling temporal point processes. You can basically model them with these sort of intensity functions that control how likely it is that the next event is going to take place. Is it going to take place really soon after this current time or in the future? And this is sort of the formula for a probability density that you have over at what time the next event is likely to take place. This function is parameterized by lambda here. And what we do is we learn what lambda should be via a deep network. And if you've never heard of these things before, but you've probably heard of sort of Poisson processes, e to the minus lambda x, where lambda is a constant. That would sort of be a very simple, naive point process model where lambda is just a simple constant. What we've done is we've parameterized that, making lambda a function, and lambda is a function of recurrent history of what's happened in the past sequence of events. So what can this do? Again, here's some examples of time sequence prediction on NBA games. These are sort of predicting when the next event is going to take place. Each of these graphs shows a possession in the NBA game, and the blue curve up above is the ground truth of how much time was there between one event and the next one. And down below, these little curves here These are our sort of probability distributions that we predict. Each of these is sort of a parameterized intensity function for one of those temporal point process models. And as you can see, it is able to mimic these sort of, this is a sequence where a whole bunch of events happen at a very regular frequency. Then there was a drop in frequency, then all of a sudden a spike. The next event took a long time to happen. And again, our model seems to be able to learn a bit of that kind of jagged nature to when the next event is likely to take place. We can also use these models to predict where events are going to take place. This visualization is showing, again, each of these colors is a possession in a basketball game. So the red one is one possession, the green one is one possession, the purple one is one possession. The dashed lines are the ground truth of where the events happened along this sequence. So again, there are these discrete events like a pass, protecting the ball against an opponent, taking a shot. These are sort of the events that happen along the sequence. These arrows show the predictions that our model made spatially about where we thought that these events are likely to take place. And again, what's happening is that it's again pretty reasonable that there's actually probably a pass from here to here. Our model predicted it would take place at this location. We actually have a full probability distribution. We don't just have that single point estimate, but we're showing this as a point estimate for visualization purposes. So again, we can actually parameterize a probability density over where we think spatially some event is likely to happen in the future. Okay, so those are some things we can do with current models for group activity prediction. Just to conclude, this segment of the talk is about understanding kind of the big picture of activity scenes. So with videos, especially with lots of people in them, with objects, with scene context, trying to use all of that to understand what's happening to the people in the scenes. It's a more holistic view of activity understanding. Again, I'd like to sort of highlight some things that I think are really important and are likely fruitful grounds for future research in this area. One of the things that really hurts you in this group activity setting is this limited data set and generalization to unseen compositions. Right? So there's this kind of combinatorial explosion problem where if I say I want to see a basketball game where there are, 3 passes, then a shot. The passes take place in these locations, then there's a shot, then there's a rebound, and then they kick it back out and they take a 3-pointer. There's this sequence of events that has to happen. And it's very difficult to imagine getting enough training data to really have seen all of those things before. If you look in the surveillance context as well, you'd like to be able to do things where you say, I'd like to have someone pick up a suitcase and walk in this direction while accompanied by somebody else. And again, having enough training data, purely supervised versions of this seems very difficult. Pooling operators. So again, I highlighted some examples of honestly kind of naive approaches to pooling nearby people. So you say, here's a person, pool him or her with the people who are spatially nearby, do some binning. Doing relational reasoning, where you reason over this person is likely to be related to that person way across the room because of some feature or something that I know about this scene. Those types of models would be very powerful and useful for group activity recognition. The other side of things is that when I said, we can recognize which NBA team this is. We have, 25% performance on a single possession, etc. We have done some visualizations of which aspects of these plays seem to be indicative of a particular team being present. But again, grounding recognition results where you say, I believe that this scene is a pick and pop basketball play because I saw these particular players doing these particular actions. That's something that we really should work on more. Who in the scene is providing evidence for some group activity taking place. The other thing is that predictive models actually capture uncertainty. There's a lot of entropy in the distribution over what will happen next in these scenes of multiple people. We'd really like to have models that can capture that uncertainty at both the individual and group level so that we can have probability distributions over what's likely to happen next and use those for making good inferences. Okay, so I'll stop there. If anyone has any questions about this package of work, I'm happy to answer it now. Thanks. Yeah. So it's a good question. So how much history do you need, and what's necessary as temporal context is It's a good question, and I think that some of these scenarios are really sort of, for example, in the sports context, you might want to know what's happening in the game, like what's the score, what's been happening in the past in this history. All that information could be useful. To be honest, that's another really good future direction, is about really long-term memories in these processes, are something that I don't think we have yet. Right? These convolutional networks that either operate over the time sequence or the recurrent networks that have some history to them, they're really not preserving very long-term memories about what's going on in a game, for example, or in this surveillance of a nursing home, what's happened in the past. Again, I think that's another really interesting area for research. How do you handle very long-term contexts?
Do you have any intuition on what the network is actually looking at when it makes a prediction? So, for example, if you look at the two things, there's the gaze, there's trajectories, if you don't get the gaze.
Yeah, absolutely. So for the sports analytics stuff, we've looked at the early layers in these conv networks, and we look at sort of what types of motion patterns they're tuning to, and they really are the things that I'm motivated with, where we get these kind of W patterns, where that's sort of in XY coordinates, the person is making a move that looks like that. That's a filter that's learned early in the network. We have other ones that are just about raw position, right? They're just saying they're kind of constant filters that say, probably something like, is there a person at this location? Which is a useful thing if you say contextually, is there someone nearby me up and to the left? That's a useful thing. So as always, as you get further and further into this, we tried to find, for example, plays that were really indicative of a certain team. And so the Boston Celtics, I'm not a super big basketball fan for the record, but apparently the Boston Celtics run an offense with a pick and pop, which is some sort of pick and roll play where someone pops out. Those possessions were particularly, the network really thought those were Boston Celtics plays, for example. So we have gone and looked at sort of which things are indicative of different teams, and they seem to be kind of reasonable. But of course, there are a whole ton of them where we're not really sure what's going on. Predicting unseen combinations, right? Yeah, definitely. So we've actually done some work on building relational layers in autoencoders. So the reason I think these are useful, this is sort of, current work that's, I think it's on archive now, but we basically try to fit, in a set of people, you try to learn layers that learn a representation that can reconstruct one person based on neighboring people's representation. So it's kind of like word-to-vec type encoding of what is someone doing with respect to other people around them. And the reason I think this is powerful then is that you don't need to supervise labels on interactions between people. You can just say, find me representations for individuals that are based upon the context of people around them. And those actually are with sort of autoencoder type learning, we've been able to use those to get very good results on either action retrieval tasks. So for example, we can say things like, find me a scene that has 4 people who are standing and 1 person who's jumping and 2 people who are waiting to receive a ball. This is in a volleyball context, and we can do that with very limited, without labeled data of exactly those things before. Yeah.
Did you look at outcomes in order to then predict or recommend activity?
So did we look at outcomes?
Yeah, to improve a team.
So I will say there are companies that we work with that exactly do this. Right? So this world is very sophisticated now, and the company SportLogic that I mentioned, I work with them. They do amazing work on basically trades that happen in the NHL, in the National Hockey League. They support those by basically figuring out, will this player fit well with this team? So you can even do these predictions which say, if I took this player out and put in this other player who tends to behave this way, based on all these data that we've done, you can predict, will that have a positive effect on the game? So yeah, this stuff is very sophisticated at this point. And those are not in our published papers, but this is what companies do based on this. Okay, well, I'll probably conclude now and let Nicholas take over. Thanks.
Okay. Hi everyone, my name is Nick Reinhardt, and today I'll talk to you about some of my work on learning to forecast agent behavior with visual data. So it's a little bit different than recognition side of things, but I'll talk about how they're connected. Okay, so just imagine intelligent agents in their natural environments. They generally follow some rational behavior. So to achieve their goals, they have to generally reason about the future. Therefore, to build artificially intelligent agents that also behave rationally, we need learning-based models to predict the behaviors of agents. So an understanding of the future will make robots safer and more reliable. In this work, I consider the problem of building behavioral models to forecast the future actions of agents. So we want to take in data from agents, for instance, expert demonstrations. They're showing this how they go about achieving their goals, and use this data to build predictions, or to build predictive models of the agents that we can apply in new scenarios. So we want our models to take as input state, or some contextual information, and output actions. We use the notion of a policy in sequential decision process frameworks to model behavior. So policies have several benefits. A policy is designed for sequential reasoning. A good one has factored in longer-term consequences of its next action. Second, a policy also encodes an agent's preferences in terms of its distribution. This distribution directly gives the agent's future action in terms of what it will do. These two properties, along with the extensive literature of policies as models of behavior, motivate us to use them for forecasting. So the task of forecasting is different from, but related to, the task of recognition. In terms of forecasting, I like to think of recognition as the task of identifying the state of the agent using data from the past and the present. While one could use also future data to recognize previous states, that model is not a valid policy. A policy reasons causally, and by that I mean it can only be informed by what's happened so far. So learning a policy requires many design choices. Each design choice imposes specific settings and comes with its own pros and cons. Our work can be framed in terms of an exploration of the space of design choices for forecasting with policies. Let's look at the main choices. First, we could either learn a policy from batch data or from a stream of data. A batch learning approach has the advantage of being easier to construct, and it's a more standard setting. However, an online learning approach allows us to continuously learn and use a forecasting policy. So I use this setting synonymously with the lifelong learning scenario. A second important choice is between discrete and continuous actions. Discrete actions are usually simpler to use and model. However, they come at the price of modeling expressivity. Many behaviors of agents cannot be precisely described with a small set of discrete actions. The next important choice is of the state representation and whether it's known or unknown. By assuming it's known, it enables us to employ algorithms that specifically use the state representation as part of their design. However, in some cases, it's either unknown or not fully observed, or we don't use a model that leverages the state representation to do most of its reasoning. The fourth design choice is whether the environment is interactive or not. In a non-interactive setting, we can't execute our policies to observe new data. This is the passive setting, which is common in computer vision. In the interactive setting, we can execute our policy directly on the environment, which enables us to collect new data and observe performance. And the final relevant design choice is the number of agents in the scene. In many scenarios, we restrict our modeling to just a single agent. And this is true in everything that I'll present today. Okay, so we're going to treat the first row of these choices as the default settings. These generally correspond to easier, more well-explored scenarios. And extending approaches to the non-default scenarios is the focus of this talk. In part one, I'll begin with extension of batch forecasting to the online setting. Then in part 2, I'll discuss an approach we developed to use a continuous policy as part of a generative trajectory forecasting model. In part 3, I'll discuss our approach for sharing a representation of forecasting with a representation of unknown state used to solve some other task. So we begin with learning a policy in an online learning scenario. In this setting, the policy must be able to make predictions at any point during the learning process. And what we use is online inverse reinforcement learning to do this. This work won the Best Paper Honorable Mention Award at ICCV last year. So here's an image from the point of view of a scientist. So how can we answer the question, what will the scientist do next? So it's hard to know with certainty. We probably need a probability distribution, but we should be able to make informed predictions about the future by watching what the scientist does. So, by watching what the scientist does, we can collect what's called as expert demonstrations from the scientist. And now I'll just step through a quick example of forecasting a person's future in a home environment. So here it's just visualized as a blueprint, and now with a 3D reconstruction. As the person moves through the environment, we capture their behavior with a first-person camera. We use this video to continuously update a policy-based prediction model. The model is used to forecast future goals, and this can be thought of as sort of what is my intent. They're colored by the probabilities here. So after I start the video in the top left, the person is going to pick up that mug, and then the goal in the kitchen will turn red. This means our model becomes confident that the person will go to the kitchen. So now we visualize the person's point of view inside this 3D reconstruction. And we see that they do indeed arrive at the model's likeliest goal in the kitchen. Okay, so to motivate our choice of inverse reinforcement learning, let's first look at reinforcement learning. Quick refresher. In RL, an agent receives a reward for every action taken. In this sense, the rewards are given. Whereas in inverse reinforcement learning, rewards are learned from demonstrated behavior. So this is a major difference of our approach from the reinforcement learning approach that learns from rewards. Our approach is not given the rewards, it's instead given demonstrations from people. The learned reward function can be used to forecast the future actions taken by the agent. However, both IRL and RL assume access to the environment. In order for our IRL approach to forecast without access, we must instead build a representation of the environment. So as an aside, I'll get into the details of inverse reinforcement learning for computer vision this Friday. I've organized a tutorial with Kris Kitani and Paul Vernaza, so you guys, if you're interested more in the details, come check it out on Friday. Okay, so there are a few veins of other related work to human activity forecasting. One approach is to just predict the future motion of a person or object. Another method attempts to predict the next short-term action that will occur. Another approach is to just predict future pixels that you're likely to see. So pixel appearance or predict pixel motion in future frames. And finally, decision theoretic approaches are relevant to forecasting and are fundamental to reinforcement learning and inverse reinforcement learning. IRL approaches have been applied to the batch data setting to estimate the policy of a person and use this representation to predict the person's future movement. In contrast to these approaches, and what I'll talk about next, we're doing online inverse reinforcement learning, where we're forecasting before all of the data has arrived. So we designed an IRL method for the task of predicting the goals of a first-person camera wearer. We jointly learn the behavioral and environmental models, whereas other IRL approaches assume the environment as prior knowledge. And so what this means is we have to track the person's state continuously as they go about their activities, as well as discover their goals. And to track this state, we use common computer vision algorithms like SLAM, and also we employ activity recognition. Like I mentioned before, we can use this activity recognition to build our state representation. And finally, our method learns and forecasts online in a self-supervised fashion. So, given this first-person video, our approach continuously models and forecasts the person's future goal. Okay, so what is a goal? There are many possible representations, but in ours, a goal consists of a 3D location, as well as information about what objects a person holds. In our previous example, the person started in the office and then took the cup to the kitchen. Their goal was to be in the kitchen with a cup. In this sense, a goal is a specific joint configuration of the user and the environment. It's a state in a high-dimensional state space of all possible configurations. There could be many goals in the environment, which means that the set of possible goals is a subset of all possible states. A person is always in a single state at any point in time. Some states are not goals, so a person generally wants to move from the non-goal states to the goal states. The person moves between states by taking actions, such as changing physical locations, or by picking up or putting down an object. Formally, we infer several hidden components of a Markov decision process. We discover the goals that a person has, and I'll get to how we do that later. In order to achieve goals, a person follows specific transitions between states in the environment. We learn these transitions in order to infer the reward function and the policy. Rewards encode a person's preferences. They may prefer one route to another, or prefer one object to another. The estimated rewards are then used to recover the policy of the person. Based on the MDP, the task is to continuously update a probability distribution over a person's future goals. So making this prediction requires several components, including our set of learned goals, a partial trajectory tracked through the state space, and it requires our learned reward function. Back to our example of the person in the office, with no partial trajectory observed, our method may produce an uncertain goal distribution over the bedroom and the kitchen. After the person grabs the mug, the trajectory grows, and the prediction becomes more confident that the person's goal is in the kitchen. Okay, so how do we learn this model? We use the framework of maximum entropy inverse reinforcement learning as the basis of our approach. In this framework, trajectories from a dataset of demonstrations are used to maximize the likelihood of a trajectory distribution, which is a Gibbs distribution defined in terms of parameterized reward function. The policy can then be recovered from terms computed from the reward function, and so you can sort of think of the policy and the reward function as being sort of one object for forecasting. In our setting, we want to forecast and accumulate demonstrations continuously. In online learning theory, one way to measure the performance of an algorithm is through its regret. Regret measures the difference between the loss of an online learner and the hindsight loss of a batch learner. A small regret means that the online learner performed well with respect to a learner trained on all of the data at once. Okay, so we proved that our algorithm is no regret, which means that as demonstrations accumulate, the time average regret approaches 0. Despite the fact that our model has to make predictions without all of the data, its online performance approaches that of a model trained with all of the data. So in our experiments, we also measured this average regret. Here the x-axis is the demonstration index, and the y-axis is the average regret. After the first few demonstrations, the method is still learning about the new goals and behaviors that the person demonstrates. Once the person starts demonstrating behavior similar to previous behavior, its regret begins to diminish. Okay, so this provides a little bit of evidence that our proof of no regret will hold in practice. And this means we probably don't have to worry about being worse than a batch model that's seen all of the data. We don't have to see all the data to begin forecasting. Okay, so how does our IRL approach that I just described to you fit into the overall algorithm? Like I mentioned before, there's some state tracking that's going on. Let's step through a visualization of each component. We continuously track the state of the user with SLAM and activity detection. The state is visualized here, projected to 3 dimensions as a green sphere. As user demonstrations are observed, goals are discovered with a stop detection procedure. So essentially, if a person stays at any place for a long period of time, we assume that that's what they wanted to do. They wanted to be in this state. We continuously forecast the goals of the user, illustrated here again with the colors corresponding to the probabilities. So the red office indicates that our model is confident that the person's goal is in the office. At every goal, the model is updated, and at every state, a new forecast is made. We evaluated our method on a data set of separate environments that we collected. our evaluation measures the likelihood of the true goal under each model's prediction. We built several baselines that rely on our state tracking and goal detection approaches, as this was a task that hadn't been attempted before. And so we observed that our model outperformed these other baselines that we constructed. Our method has the benefit of explicitly reasoning over the state space and graph of possible behaviors with our online inverse reinforcement learning approach. So to summarize, we designed an online method for the task of learning a policy and predicting the goals of a first-person camera wearer. One key limitation, however, to this forecasting approach was that it made the assumption that actions are discrete, and as a result, the model is fairly coarse. The person being modeled actually exists in a continuous world. Trajectories sampled from this policy look jagged and unnatural compared to the real trajectories from the person. This motivates our next choice. Now we want to learn a continuous model of sequences of behavior to forecast the future. So we investigated this in our following work. We want to learn a generative model of continuous behavior. The setting we use here is the vehicle forecasting scenario. A data set of human demonstrations driving a car is given, along with visual data for each scene. The task is to forecast plausible future trajectories in new scenes. The approach we use is to parameterize a generative distribution with the rollout of a learned policy. So essentially the distribution factors in a behavioral model. Our model has the benefit of being able to perform exact inference, meaning that we can compute the likelihood of arbitrary trajectories. So our first goal with this approach is to predict the future with a generative distribution. So in this figure, the left image shows part of the input to our method, which is images taken from a car-mounted camera. On the right, the true future, or the expert demonstration, is shown in blue, and samples from a learned model are shown in red. These are both overlaid on top of LiDAR, which is also collected from the car. So we have a secondary goal, too, to be able to learn and quantify our model efficiently and well. This means we want to learn a model to both sample well and to quantify the likelihood of its samples. Other generative samplers are relevant to this problem. However, many of them cannot precisely quantify the learned distribution in terms of likelihood. Methods such as VAEs and GANs don't admit a way to efficiently compute the PDF of arbitrary data. This is important when we want to evaluate the model on held-out data. If all we can do is generate samples, we're forced to try to measure if the samples are good versus the more reliable way of measuring if the held-out data is likely under the model. So related to this inability to compute precise metrics is the fact that many standard trajectory forecasting techniques either do not optimize or do not quantify with good metrics. And I'll get to these later, their deficiencies. So attempting to evaluate sample metrics of probabilistic models is tricky in general, and computing L2 distance or nearest neighbor distances result in metrics with obvious failings. So in this work, we develop an approach to efficiently learn and quantify a model to produce good samples. Our approach can compute the exact likelihood of trajectories from held-out scenes, and we identify some issues with other trajectory forecasting metrics. We also collected a new data set to forecast ego vehicle behavior that's several times larger than the KITTI data set, which is the standard data set that's being used for vehicle trajectory forecasting. Our data set was collected in California and specifically created with the task of vehicle trajectory forecasting in mind, and so therefore we call it the Cal Forecasting data set, and we're going to make it public. So we find that our main model, R2P2, achieves significantly better performance than these related approaches, a few other related approaches across all the data sets we tried and metrics we evaluated. And we demonstrate that the form of our model can be used to replace the policy in an existing model-free imitation learning method. So imitation learning is one way to learn policies from expert data. So this improved approach that we constructed is different than our primary non-adversarial approach, R2P2. Okay, so how should we represent a single future? Here we consider the 2D position of the vehicle as its state, and a fixed length sequence of states to be a possible future. Because the future is inherently uncertain, like our previous approach, we use a distribution over possible futures. Demonstrations of driver behavior are then assumed to come from some unknown distribution over future behavior. Okay, so I'm going to skip that. In order to approximate the true distribution, we must choose some divergence metric that measures the difference between distributions. We want to be able to efficiently compute and optimize this divergence metric that we choose. So a common divergence metric that people use is KL divergence. Minimizing forward KL divergence is equivalent to maximizing likelihood, a very standard approach to supervised learning. Maximizing likelihood of samples from the true distribution. It's also equivalent to minimizing the cross entropy from P to Q. So I'm going to build an objective in terms of those cross entropies, these H terms, instead of this KL divergence. There's a significant issue with only using KL divergence, however. It does a bad job of penalizing poor quality samples. So let's say I have some good reference model for P. Here the red trajectories are samples from the learned model, and the blue trajectories are samples from the true data distribution P. This model receives some good low cross-entropy score, M0, and now let's consider moving half of Q's density away from the true modes of P and putting it somewhere far away from the demonstrations. Q now generates some bad samples, and the forward cross-entropy is only penalizing the model around the demonstrations, and it's only going to yield here, in this case, a small penalty of log 2. Yet half of Q's trajectories are now very poor. Therefore, the forward KL divergence is insensitive to generation of bad samples. And this is a known issue in some works. So what if instead we reverse the order of the arguments to the KL divergence? So KL divergence is not symmetric. It depends on the order of the arguments. This would make samples from Q likely under P and prune out the bad samples of Q. It corresponds to minimizing the reverse cross entropy and maximizing the entropy of our model Q. So there's a major issue with this, however, which is we generally can't evaluate the PDF P in the first place. If we did, we would basically already be done. However, what we propose to do instead is to learn some simple, low-dimensional approximation to P and use that to penalize samples. So I'll get to what that is soon. But essentially, I'm not sure if I'll have time to cover it. Essentially, we learned something that penalizes going off the road. 5 minutes, okay. So, let's see. Maybe really quickly I'll talk about some issues with some trajectory forecasting metrics. If you just use L2 distance, you can get the common problem of regression to the mean. Or if you use nearest neighbor L2 distance, so only penalizing the samples that are closest to the demonstrations, it's sort of a similar failure mode to forward KL divergence. You can generate a few good samples and many bad samples and you won't be penalized for it. So what we do is we just combine the forward and reverse cross entropies because it ensures that our model both learns to assign high likelihood to the demonstrations as well as generate good samples. And here, you can think of the green grass as being cost that we learn to penalize samples that go off the road. Okay, I'm going to skip along. Skip this. Okay, we measured some performance. Note, again, I said many models have some issues with actually doing exact inference or computing likelihood. So in the CVAE model, that's the previous state-of-the-art, you actually have to approximate the likelihood by sampling from it many times, versus our model, you can compute the PDF in one shot. And so we find our model does better. Let's just look at some examples. So here's some overhead LiDAR, and it samples from our model as well as the true future. And this is this P or cost map that we're sort of learning. And then we show this as projected to a first-person camera mounted on the car. And note what it does at intersections. It will generally produce diverse samples, and that's because the forward KL divergence is ensuring that you put probability mass to cover many of the diverse futures. And note that the samples generally stay on the road. Okay. So, let's see. How much time? Okay. All right. Not too much more time. I'm almost done. So we focused so far on settings where the true state is fully observed. But now we want to think about, okay, so what if we don't actually know what the state of the agent is? What if it's only partially observed? When the state is only partially observed, or you don't model it explicitly, the problem of learning a good policy is generally harder. So we use a continuous policy framework in non-interactive and interactive settings, but our focus is on handling the non-explicit modeling of state. So this begins the next section, which I presented at NIPS last year. So our idea here with this next work is to improve the learning of policies with a straightforward tool. Encourage the policy representation to be predictive for the future, in addition to its primary task objective. If the policy's state representation is poor, it will not have enough information to predict the distribution over future observations. If the representation, however, is good for forecasting, it's likely to be good for performing the control task itself. So in standard RNNs, there's no direct supervision on internal state. In RNNs, the hope is that the internal state somehow learns to model the underlying hidden state of the dynamic system being modeled. In our approach, we use supervision from the future to better learn the underlying policy, but our idea can also be thought of as a way to better learn the internal state of general RNNs. We add supervision from future observations with what we call a predictive state decoder. So essentially, it's just going to penalize the state representation of the RNN from failing to be predictive for what you're likely to see next. And so with that idea, you just do a multitask learning objective, and you essentially, I'll show you, you essentially outperform not having this predictive state representation. So we evaluated on some imitation learning and reinforcement learning benchmarks, and we found there are many settings in which our approach improves performance. So basically, if you want to learn a policy and with some unknown state representation, you can use a really simple trick to just predict the future, because the future is an equivalent representation of state if you have a good idea of what the future is. Okay, so in contrast to many reinforcement learning works that struggle with significance, we performed hypothesis testing by running experiments many times. So we found that in a variety of settings, our approach led to a statistically significant improvement. Okay, so I guess I went a little fast there at the end, but this concludes my talk on learning policies for behavior forecasting. So I work on a few other overlapping topics, including reinforcement learning, IRL, and structured prediction. Okay, so a huge thanks to my collaborators and many other people, and check out my website for more details. I generally keep it updated with my latest work. That's it. Any questions? Okay.
Okay, thanks for staying with us. And before we conclude, before we hear the closing remarks from Greg, let me try to entertain you for like just 5 minutes, showing you fancy videos of something, some of the topic which might be a bit different from what you have seen so far today. So this is particularly about privacy preserving action recognition. And what the hell do we mean by privacy preserving? So, so far we didn't care about privacy at all. But in some of the applications, we are really concerned about unwanted video taking and sharing. The cameras are becoming available in private places, like smart home cameras, robots, and so on. And we want to remove, or we want to minimize the potential risk of one's videos being monitored by a hacker, company, or government. So we want to at least prohibit the recording of the videos with identity information. And that objective is actually contradictory to activity recognition, because activity recognition means that we want to have as high resolution data, as detailed data as possible, and we want to also access high performance cloud server, and all these are very contradictory to protecting the privacy. So we need a solution. I mean, I just wanted to bring your attention that this is a problem. This is another problem which is kind of, in parallel or independent of all the issues we have discussed so far, and we need to find a solution. One possible solution is simply prohibiting the use of the camera devices and robots, which is a pretty bad solution in my opinion. More intelligent solution will be to anonymize videos. At least remove the identity in videos so that the human cannot be recognized by other humans or by the model, CNN model. So such as adding noise, blurring, masking, completely masking, and so on. The problem is that these types of optimizations are handcrafted and they are not optimal. So the main idea in this particular research direction was to learn to anonymize videos optimally in order to maximize the privacy protection while also allowing recognition. So here's an example. This is a real example based on our anonymizer which was learned. So we were able to convert a human's face into another face while preserving the object information related to the activity, such as toothbrush. It doesn't look too, it looks quite ugly. So let me show you a better example. And this is a better example. Left-hand side is the original video. Right-hand side is automatically converted, whatever video. So we have no idea who the identity is, but the information, lipstick, that is actually preserved. So of course, we are formulating this in adversarial network, where we have a video anonymizer and action recognition collaborating each other so that we want to modify videos to prevent face recognition while maximizing action recognition. And we have the competing system, which is face classifier, trying to find who the person is. And yep, it's scan. Multitask scan, actually, with multiple different losses. And I will not go into this, but I will show you an example. Left-hand side is the original image. Right-hand side is automatically converted, automatically anonymized faces. Anonymized faces from videos and anonymized faces in actual video example. So we are showing the original, our conversion, as well as previous handcrafted blurring or just masking. So even if we mask, we are able to sometimes tell what activity that is, but the recognition accuracy is much lower. So the idea was to preserve activity information while getting rid of face identity. And we were particularly fooling a particular face classifier, CNN classifier. And a bit more quantitative result. So x-axis here is face verification error. It was a binary test telling whether two faces belong to the same person or not. So the best scenario will be that it's totally confused, and the best scenario will be 50% error. Y-axis is activity detection, spatio-temporal activity detection, mean average precision. So if the point is at the top right corner, that means the best. And as we are able to see, the triangles learning to anonymize are performing quite a bit better, doing better face anonymization, better recognition compared to masking or adding noise, blurring, and so on. And some of the faces of celebrities you may be able to recognize. And yeah, these are just the output of the learn and anonymizer. So I will omit all these. We did a user study. We asked human to do the face recognition, binary face record classification, and the accuracy was 53. The random accuracy is 50, means that it's quite correctly anonymized. And celebrity face recognition accuracy was much higher. The chance was like 8%. And the human did much better, but that's also due to the distinct hairstyles as you see from this video. And just summary, we have many privacy sensitive data from home automation, service robots, and so on. But not much attention has been paid in making data or recognition process privacy preserving. So I just want to bring your attention that this is another problem we all need to worry about if we want to handle human-related data from private sources, which are actually quite common situations. So that's all I wanted to just mention as one of the emerging topics. Questions? Questions? No?
All right, so just some final concluding remarks about what did we do today. I think maybe one thing that struck me was there's a huge variety in different data sources that we talked about today. And so in the kind of human activity recognition, we have everything from kind of YouTube, unconstrained internet videos that are shown over on the left-hand side, charades type data sets where we're asking people to film themselves doing things. The bottom left corner is vlog. I don't think anybody talked about this today, but again, it's off getting kind of boring, everyday sort of actions off the internet. There's a lot of focus on this as well. So from that through to sports videos where you have relatively structured domains, but there's a whole lot going on in terms of interactions and group activities and many subtle things that you want to be able to tell the difference between. And then into surveillance context over on the right-hand side, as well as first-person videos. And these are the challenges in doing activity recognition. We have video source variety, we have structured outputs, structured inputs, we have lots of interactions going on, there's scene context, object context, multiple labels that need to be put on a scene, etc., etc. So those things we talked about, and I want to kind of leave you with one sort of, where I think is important for this field to go is about really getting this holistic, total labeling, total understanding of the entire scene. And so at the beginning, we talked a lot about video classification, video tagging type of approaches. So we had a short snippet of video like this. I want to put the tags on them, such as this is a volleyball game, it's US versus China, it's an indoor scene, it's the first set of this game, it came from 2014. Data sets like the YouTube 8 million data set, these provide often really very specific tags that go with a video that apply to the entire level of the video. Beyond that, we talked about action localization spatio-temporally, as well as group activity recognition, putting labels on the individual people. We go further though, we could talk about doing semantic segmentation in videos. We like to know that those pixels correspond to the crowd, those pixels correspond to the court. Knowing what every single voxel in this video is about is important to understanding the entire context. And then we heard from Nicholas about predictions. So what's going to happen next? Trajectories of players, trajectories of the balls, what activity is going to take place next in this scene. We like to be able to do all of those things. And so I think what's exciting about activity recognition is that many of these challenges are unsolved. Neither do we have the data sets that support this type of reasoning, nor do we really have the right definitions for these tasks. And so I've sort of, highlighted a bunch of things that throughout the day I've sort of thought about as where I think are interesting grounds for future research. And really, there's a lot more that needs to be done in terms of fully understanding every single voxel in a video and doing that at the multiple levels of detail that we need in order to be able to say that we've sort of fully finished activity understanding. Okay, so that's the very, very quick conclusion of the day. Thanks very much for staying through it, and I hope you enjoyed it. If you have any more questions for us, I'm happy to take questions, and Michael and Nicholas are up here as well. So thanks very much. That's the end.